All right, welcome to another exciting episode of AP Chemistry here at Spain Park High School. Today is Friday, January the 31st. It is hard to believe that January is already over. We're almost done, y'all. We get to spring break, then everything's going to be review after that, ideally. So, I mean, we're cruising in and working hard. Okay, we're getting there. So, today we're going to be talking more about kinetics, rate laws. We've talked about the differential rate law. We're going to look at some simple problem, actually the next step up type problem. We've done the simple rate law problems. Do one type of kind of crazy problem, looking at the work that you did in class yesterday. And then we're going to start talking maybe about the integrated rate law, kind of going the other way. Instead of it being concentration related to rate, it's going to be time related to rate. And so we're going to look at that. And then once we finish dealing with the integrated rate law, then we'll start talking about just reaction mechanisms and what they are and how do we use those in the reaction. And then we're pretty much done with this unit. We will be doing a lab next week, probably Tuesday of next week. That way I can remind everybody on Monday to make sure you wear the appropriate clothes, and since there's so many people out today as well. But it is it's one of my more favorite. It's one of my favorite labs that we do. But we'll see if it is yours. But the math, I'm going to tell you, it's going to be a math intense lab. But we'll do the lab on Tuesday. We'll spend all day Wednesday just kind of talking and working the math on that particular one. There's going to be a lot of data in this particular lab. Okay. So the first thing I want us to look at is in your packet. This is page 3, the one I just gave to you. And this is just a graph of the concentration of reactants and products over time. First off, if you just look at this graph, which one of these do you think is the reactant?
The green line.
Okay, the green line, okay? Because it's starting here and it's decreasing. But on this one here, so here's your equation down here that it's graphing. Why is the blue line twice the red line? Okay, because the rate of formation of this is going to be twice the rate of formation of the oxygen. So when we're looking at the graph, notice that the NO is coming down at the rate of decrease of this is exactly the same of rate of increase of that one. Because it's the 2 to 2. That's the relative rate law type graph. So I just want you to make sure that you can understand how the graph works. Are we good with that? We see how that all works? Oh, she's having a little spell back there. That's all right. Okay? So I just kind of wanted you to see again. We looked the other day just at this part of the graph, but this one is good as far as showing how the products also change, going from 0 to wherever they're going to end up at. Okay? So we just, again, graphs are always going to be important. So let's get to the worksheet out that you worked on yesterday. Okay? And I'm going to give you some grace here, because if you didn't do them all, then you're still going to have some time. I'm not going to come by and check those. I know, I'm going to give you credit, but I'm just saying I'm giving you grace that if you're not finished, I'm going to check them later. Okay? But if we look at, I've already spent too much time checking grades. I should have checked that at the same time. So if we look at number 1 on page 558 on that packet, okay, we can see how the rates are going to compare with one another. This is just relating all of the rates of the reactants and products in one big equation, but the net result are these values. Okay? Does everybody agree with that? Does anybody have any question on that? Does everybody understand that? Does everybody understand this? This is always, now what does the negative sign mean?
Disappearance.
Okay, the rate of disappearance, okay? Okay, so the rate of disappearance is given in the problem. The rate of disappearance of the S2O3 is that rate. But then you just use the coefficients from the balanced equation. Okay? So there's a 2 in front of the S2O3, is there not? Okay, so when we look at that, where is mine? It's right here. So if I look at the equation, there's a 2 here and a 2 there. So that means, in terms of this, here, is this what it's measuring in, the rate of appearance of that? What's the original rate at the top? Okay, it says right here, point is consumed in 1 liter per second, the S2O3. Okay, so here's the rate of this. How is the rate of this going to compare to the rate of that? Just in general terms. It's going to be half. So if this is being consumed as 0.008 moles per liter per second, this is going to be consumed as 0.004. This is going to be formed positive 0.004, and this is going to be formed appearance 0.008, right? That's all that's saying. Okay? So we're good there. So now if we go to page 512, we look at number 31. Okay? We do our, and a lot of y'all are struggling with this, just in the data table, it's labeled rate. So that's the number that goes with rate. Okay, we're seeing how the change in rate, and if you have 3 of them, now I know there was a lot of confusion on this one because H plus was also in the products. But if you look at the arrow, if you have the sheet in front of you, you look at the arrow, it says acid catalyzed. Does it not? Isn't that the one that says acid catalyzed? Yeah? Okay. What element is present in all acids? Hydrogen, or which ion, I should say, H plus. So yeah, the H plus is a product, but that's not the H plus that they're measuring. They're measuring the H plus of the catalyst. You never have products in your rate law. You're only going to have the reactants in your rate law. But it's because H plus was a catalyst, so we have all 3, X, Y, and Z, and you just do them all the same way. Did we all get those values?
Yeah.
Now some of y'all may have done it the other way. You may have done 5 to 1 here and did 3/4, 0.75, but it'll be 0.75 equals 0.75 to the X instead of 1.33. Okay? Are we good there? Any questions? Does everybody know where all the numbers are coming from? And then we go through and calculate the rate. It's first order with respect to that. We'll talk about what 0 order means. In general, what 0 order means, anybody want to venture a guess? Did I tell anybody yesterday?
It doesn't affect,
What doesn't affect?
Doesn't affect the rate.
Okay, the concentration doesn't affect the rate. Okay, concentration, so it doesn't matter how much you have, and we'll talk about the why when we get into reaction mechanisms. There are some steps that are fast, some steps that are slow. If the reactant is not in one of the slow steps or in the slow step, then it's not going to affect the rate, and we'll talk about that more later. All right, and then the overall order. How do we find overall order? Adding. Okay.
does it matter for answers on scientific notation?
Absolutely not. Absolutely not. It's the exact same number. 2 different ways of representing the exact same number. Okay? Whatever floats your boat. All right. So, yeah.
Where did you see 30?
Yeah, but I don't have the answer for that one. What did you get? What did you guys get for the answer?
There were multiple.
Why
I was
is
just wondering
2
what
and
what
X
it
1?
means when it says, could this reaction occur in a single step?
Okay. We'll talk more about that in terms of the mechanism again, but there's a thing called molecularity. It's all based upon the order, what the order really means. If something is first order, that means only 1 molecule of it is involved in the chemical reaction. If something is second order, that means 2 molecules have to collide. 2 of that same molecule have to collide and do something. So if it's a third order overall, if it's a first order here on this reactant and second order on this one, that means you'd have to have 3 molecules collide all at the same time, we're all with enough energy to overcome EA, all with the proper orientation to form an effective collision. Which then the probabilities, the more molecules that have to collide at once, the lower the probability that it's all gonna happen. The slower the reaction's gonna go. So the reality is that first and second order reactions could possibly occur at once. Anything over than a first or second order probably is not gonna happen in one step. In our reaction mechanism, when we start talking about those steps, we're gonna have an elementary step. And an elementary step is just what you see is what you get. And again, that when we get into mechanisms, we'll get into that answer a little bit more deeply. But I could get way into the weeds right now with that. But let's just put that on hold. All right. Do you have your work? I can probably read your work. Do you trust your work? For number 30?
Yeah, you can find what that is.
Okay, let's see. So the third order, since it's a third order reaction, what would you say then in terms of, okay, would it happen in one step? Most likely not. Most likely not. Anything over second order. And there was an AP question a few years ago that it was a sixth order overall. And they asked this question, do you think there's just no way that 6 molecules could all collide in the proper orientation with all the right energy at the same time and happen? Okay? Generally nothing over a second order would happen in a single step. But you cannot just look at a reaction and say it's gonna happen in a single step. There's no way to know. Most of the time it's not, okay? Does anybody have any question on 30? We all good on that? We just did 31. 33? Are we all getting the same answer? Yeah? We have fourth period to 50, and then we have fifth period, first lunch is to what, 12:20? Oh, this class isn't much different. It's gonna be the same length. Yeah.
What would the units be for the constant? Would there?
If it's third order, was it third for this one?
Over meters. times-
Yeah, oh, that's true. Okay, so let's leave.
Where's
Okay, so if I'm looking at this,
Like dying.
okay, if I'm looking here, it is, this is my rate law, right? So here's K, so this is gonna be molarity, and this is gonna be molarity, so I'm gonna end up getting molarity squared. But this is always molarity, and what is the time per second is the time per second. Always check what the unit of time is. All right, because most of the time it's seconds, and sometimes we just get in the habit of per second, and then we miss it because it was really per minute or per hour. Okay, so one of these meters cancels out, which means that when this comes over here, we're gonna have seconds times molarity. I said meters, molarity. One of the M's, molarity is going to cancel out, so we're going to have molarity squared on the bottom. So it's going to be 5,000 seconds times molarity squared, which you could say 50,000, okay, seconds to the -1 times molarity to the -2, or you could say 50,000 where we have liters squared over moles squared times seconds. Either one of those are legitimate unit ways to express the units. You'll see,
We think D's wrong.
Yeah,
okay?
she forgot to add the K value.
Oh, we've got
I did
K.
it.
Oh, come on,
Yeah,
sure.
it's 0.2.
Okay? So what is K? K is equal to 50,000.
Yeah.
So it's gonna be 50,000 times this,
Yeah.
divided by this.
Yeah, 0.2.
Okay? So it's gonna be 2,000 divided by 50,000, which is gonna be 0.2.
We'll have to do it,
Well, it was, you got like 0.4, but you had square rooted, so then you got 0.2. Because the D squared.
Okay.
It's a spring.
That,
Yeah.
okay?
Just so,
Yeah,
it doesn't really matter, but that one's actually for minutes instead of seconds,
Yeah.
so.
What?
That's fine.
Oh, man.
well, that's what I gotta check, okay? We cannot assume it's seconds. Okay?
This thing's kind of.
Will you get like the whole problem wrong? and get the-
Well, if, that's a good question, because if it's a one pointer, if it's only a 1 point question, you know, calculate K with the units, then yeah, you missed the whole thing, because you didn't have the units right. Okay? And that's, again, I said to always check, and then you said, oh yeah, it's seconds, oh yeah, it's seconds, and then somebody finally checked, and it's minutes. Okay, so it's gonna be minutes, it's gonna be minutes, and it's gonna be minutes. Okay, you must check. Alright? So, and what would the units be on B? With this one here, when we're getting
Square-
this?
or Molarity
Just-
squared per minute.
No,
Wait, oh, D, I think.
you know, for D, what are the units gonna be for this?
Molarity per minute.
Just molarity, right? Concentration is always gonna be molarity.
Oh, yeah,
Okay, so we always wanna get in the habit of using
yeah.
our,
I'm still looking at the wrong question.
we still wanna get in the habit of using the right units, and then just comparing 34. This is a long one, huh?
Yes.
We all good on this part? Yeah,
Yeah.
okay? And then 35. All right, now again, let's talk about units. This is gonna be, now what is the time on this one? 35,
Meters per second, or mole over liters times second.
okay? It's moles per liter per, so it's molarity per second.
35 is just entirely wrong.
Yeah, you need a Z. There's no Z.
Okay, well, that's, okay,
Each component of the reaction, not the reactant.
right, and so that, again, that's going to be, okay, who feels like they got it right?
Me.
That, but I can't,
Oh, you can read my handwriting, Professor Pops. Please, I look good. I'm glad I did. I did this all like 30 minutes ago, so you know what I'm talking about. I asked for answers.
okay, now look, if they give you 3 reactants, 3 things in the data table, you need to use them all. Okay, we need to use them all. And hey, it's no big deal if we got it right or wrong, okay, that's why we're doing these practice.
Okay, hold up. For Z, you get 1 equals 1 to the Z. Would it be 1 or 0 for Z? Because it could equal 0 or 1.
I got 1 to the, or 1 equals 2 to the C.
I got 1 equals 2.
Okay.
Yeah.
I just did that word. once.
Yeah, yeah, it's just when you look at, so when we look here, let's look at it. 35, that's 32, that's the wrong, here's, it's gonna be here. 35, which number is
It's
that?
up top right.
This one, keep going right there, that?
Yes.
Okay. So are we doing X, Y, and Z? Okay?
So, this
Wait,
is,
so-
this is
Don't you always have to do it in respect to the reactants?
Yeah. Z is a product. NO2F, that's a product.
It's, yeah, but
But if you
for
can
B,
do it
it's,
for-
it says each
Yeah, but
component
you
of the
can
reaction.
keep it constant, you don't have to, yeah.
Oh,
So you, so she was right, she was right.
Why would
Well, Z is,
It's
ends
throw
up,
you off.
Alright, hold on.
Z ends up equaling
Pause.
0 anyway, so it doesn't
Okay,
matter.
nitro fluoride, an explosive compound, can be made by treating nitrogen dioxide with fluorine.
Thanks for telling us.
Use the rate data below to answer the questions which follow. Okay,
What does us to each
They tricked
compound?
me,
okay,
it's not fair.
write the rate law. What is the order of reaction with respect to each component of the reaction? Now, and what is the numerical value of K? Now, I am not sure why they do give you the product, but you're right, you're only going to use reactants in the rate law. Okay?
It ends up equaling 0 anyways, so it would just be like a times 1.
Yeah, that's it.
So it doesn't, you can
Yeah.
do it with it, it doesn't matter.
Yeah, but again, you are gonna only use reactants. I will just tell you on the AP test, I've never seen a question like this. Just for the record, this book was copyrighted in 1987, is the book that this came out of.
This book's almost as old as you.
It's older than you.
Older?
Oh, whoa.
No, younger.
1987?
Oh,
I was
yeah.
teaching out of this book in
Stop
87 for
complimenting
5 years. So, no, in 1987, I was already going on to my second school, different, teaching, I was at Baton Rouge High. Okay, this was the book that, LSU freshman chemistry was using, that year. Okay, so we don't need that, so we have all of this. So the other, so we'll go back to this one, is probably more accurate than what you guys were giving credit for,
I told you.
okay?
It's insane.
Oh, you didn't say anything.
All right,
But she didn't put units on the kid.
but what, so, no, hey, let he without without sin cast the first stone here. He who has not made a mistake cast the first stone. I think we're fine here. Okay, so what are the units on rate always? Molarity per time.
Per
And what
time.
is the time unit?
Second.
Are we sure this time?
Yes.
No, sure.
It says that.
Okay, so it's molarity per second. So this is molarity, and this is molarity. So one of the molarities always cancels. So the unit is always going to be one less molarity than the overall order. And it's always going to be in the denominator, so it's going to be per molarity times seconds. Okay? Yes, sir.
If you had like a third molarity, would it be molarity squared? times
Always,
second?
whatever the order is, it's gonna be one less.
Okay.
Because one of them is gonna cancel from the rate, and it's gonna just leave whatever's left over here, and it's always gonna be the denominator. Okay, so now I want us to look at number 32. Feel redeemed. Number 32.
You don't deserve it.
Number 32 is here.
You should already know.
So what time do we leave?
Okay?
Oh,
That's gonna go to the top of the next one, isn't it? Okay, so here's the data. Here's the data for 32. So the first part of the question of 32, no, you were not. Well, let me just,
Is it asking for like the rate law or like that number?
okay, I'm just gonna put this up here, kinda like this. 32. Okay? See how to
You got this.
go old school here.
Mr. Hobbs,
Yeah,
can I give up piece of paper back?
oh yeah.
All the work.
Bless you.
So this is just not-
He's gonna take it anyway.
Okay, so here we go, 32. There's the whole thing on one page. One major iron irritant is smog, it's formaldehyde, CH2O.
Wait, that's
It's the one on the left.
table on the right is the one we just used.
Yeah, just scroll down to the bottom page
Bro, are you
32.
tripping?
Well, okay, let's just do that then.
Hey, bro, don't do it.
Okay? What are the relative rates of disappearance of O3 and the appearance of CH2O? Okay? So what are the relative rates? Okay, so when I look at this, how does the rate of disappearance of O3 compare to the rate of formation of the formaldehyde?
It's half.
Okay? This is going to disappear at half the rate of the appearance of this. So if this is appearing at 10 moles per liter per second, this is disappearing at 5 moles per liter per second. Okay, so that's all you have to do for anytime this key here, relative rate, that word. That's all you're going to use your coefficients. Okay? Now, determine the rate law using this data. So we can get rid of that. Now we have this. I'll just put the equation up here. And the equation for this again, and you have it written right in front of you, but it's C2H4 plus C2H4 plus, what is O3?
Right.
It's ozone. You've heard of ozone, that's a major component in smog. You're gonna get 2 CH2Os plus 1/2 O2. Okay, so there's my equation. So now I want the rate law. So what's my generic formula for the rate law? Rate's gonna equal what?
Okay.
K
And then the molarity of the reactant. And so,
to
to the X.
the X times
O3 to the Y.
O3 to the Y. Alright? So now I have to get those. So I go to my table. Alright? I want to get the O3 exponent so I can see that these two stay constant, right? So then I can say this is going to be times 3, and this is going to be times 3. So now again, I say the change in the concentration, change in the rate is going to be 3, is going to equal the change in the concentration to some power, obviously x equals 1. So I know that y, or pardon me, in this case, y equals 1. Because that's the ozone. That's what we changed. I did switch it. It's y.
Yeah.
Those fuse.
All right? Let me finish this and then I'll give you a break.
How long?
Okay? Just 3 minutes or so. Okay, so I want to get into the differential rate law. I mean, the integrated rate law. But what's the issue here? When I want to now change this one, 1 to 2, this is I can either go 1 to 2 or 1 to 2. What's the problem? None of them stay constant. So how do we do that?
You can multiply everything by 2 or something.
No.
You don't do it.
Yeah. So I'm gonna lose those points.
It's a 0.
It's not a 0.
You just gotta do it.
Do we have 2 variables?
No.
Yes.
Oh, yeah, because you can plug it for a while.
Okay, so what?
Plug it for a while.
Because we now know what y is, right? The only thing that's gonna be different on this is now that we have to include both of them, but we know now, we know what y is. So now when I do my next equation for the ozone, well actually not for the ozone, for the C2H4, okay? Now I'm gonna say the change in the rate, and I'm gonna use, because this is easier math here, I'm gonna use experiments 1 and 3, okay? Rather than 2 and 3, because they're both gonna be changing. And this way, we're going times 2 and we're going times 3. Okay, just see my logic? Pardon me, times 2 and then times 2. Pardon me, I was looking there. Okay, so I'm gonna say it's gonna equal, so I'm gonna say 1 to 3 is gonna equal the change in the concentration of C2H4 to the X times the change in concentration of the O3 to the Y, but we now know what that one is. We know it's to the first.
Well, don't we need K?
Not yet. We're not trying to figure out, we just figure out the order. Okay, we're doing the exact same thing, except this time, one of them doesn't cancel out, but we know what it is now. So now my change in the rate from 1 to 3 is times 4, right? So 4 is going to equal my change in the C2H4, which is times 2, and the change here is times 2. Right? So it's going to be 2 to the x times 2 to the first. The change in both of them. They're both, we're doubling this concentration and we're doubling this one. But we know how much this change is going to affect it. It's the first order with respect to the O3. So it's not a variable, it's not a y anymore, now it's a 2 to the 1. So I only have one variable.
So x equal 1.
So divide here, so 2 is equal to 2 to the x, so x equals 1.
Let's go.
So when you have one of the reactants that you don't keep the concentration constant, you figure out the one you know, and then you have to just put them all into that equation. Okay? Now, every once in a blue moon, they put that on the AP test. Most of the time not. But once in a blue moon they do. And so we'll look at one more practice of those and just kind of see how that works, and then we're going to move on. Okay? So go ahead and hit pause on that.
Go.
All right. So this is what I told you. There's a long way that what I'm giving you when we say the change in rate is equal to the change in concentration raised to some power. That's the shortcut. This is pages 6 and 7, I believe, in your page 6 and 7 in your packet. It kind of goes over this. This is technically the way that you're supposed to go about finding the order of the reaction. Okay? Is that you compare your two rates, but you put the whole rate law for both of the rates, for both experiments. Okay? In this case, they're going to compare experiment 1 to experiment 4, 1 and 4, and then they put the rate is equal to K, which they don't know what it is yet, but it's going to be the same, it's cancels. Okay? They're keeping the one that is constant, it cancels out, so then they're changing, it ends up being only the change in, okay? So this is really 1/2. Now, I would have done it the other way, I would have done 4 to 1, so it turned out to be a 2, okay? But it turns out then that 1/2 is equal to 1/2 to the x. We're just going to this point right here. The change in the rate is equal to the change in the concentration. That's this right here. That's that change to the x power, they're using n.
Isn't that exactly what we do, except we understand that K is gonna cancel?
We understand that the constant is gonna cancel. That's what I'm saying. This is exactly what we do. We're just bypassing all of this and just going straight to this part right here, where we get the table logic, and that's 100% fine. I'm just saying this is where this comes from.
Can we use this if it's not the same? Like if the-
Well, again, there would be too many variables again, whatever.
Well, like I'm saying, like,
Yeah.
you know how we plugged in Y last
Yeah,
time?
yeah.
Could we just set it up where we input Y into there?
Yeah, but again, it all works out the exact same way.
Okay.
But see, that's where you're doing this, but but both of them aren't gonna cancel out. That's what, so you're gonna end up having both of these things in your final determining your rate. Your rate changed 4 times, okay, when you compared them, but then we had this value, 2, and we had this value, but we knew that this was 2 to the 1 times 2 to the x. Okay, so yeah, so you're really doing this, it's just this part's not canceling out this time.
Yeah.
Exactly. But I'm just kind of showing you that, technically that's where we're coming from, where we're just using the shortcut. All right. So that is all the differential rate law, okay? If we go the other way, we have what's called the integrated rate law. Now, it all depends upon that when you take the integral of something, all the exponents are going to affect what you get. So when we look at this here, turn to page 9 in your notes, and you can look at this. And before we look at the graphs, we're going to go here. If we have a zero order, okay, that means that in a zero order, rate is going to equal to K times the concentration of reactant A to the 0 power. Okay? Which means the rate is equal to K, or K equals the rate. When you take the integral of this, okay, and you don't need to know the how, the why, or where, it turns out to equal the concentration of A is going to equal negative KT plus this little 0 always means the initial concentration. This is initial concentration. That's what's in the table. The table is always an initial concentration. All right? So notice that this says that Y equals mx plus B.
Wait.
That is a very fancy way of saying Y equals mx plus B. What is the shape of the curve for a line, for something that has an equation Y equals mx plus B? It's a straight line, it's linear, okay? So if something is zero order and you plot concentration versus time, you're going to get a straight line, as you can see right above on your paper. Now if it's first order, and those of you in calculus, have you guys done integrals yet?
Yeah.
Okay? So we have the rate is equal to K times concentration of A to the first. Now when I take the integral of that, you're going to get this equation. The natural log of A, it actually comes out and you rearrange it to this, but the natural log of A is equal to negative KT plus the natural log of the initial concentration of A. Again, Y equals mx plus B. So now if you plot the natural log of concentration versus time, and you get a straight line, then from the graph we can tell that it's a first order reaction, just from the graph. And then lastly, if it's second order here, and I take the integral of it, it turns out to equal 1 over the concentration of A is equal to Y equals mx plus B. So your Y is equal to 1 over the concentration. The Y-axis is always going to be, if it's zero order, it's just going to be concentration. If it's first order, it's natural log. If it's second order, it's 1 over concentration is equal to, versus time, mx. So time is always going to be your x-axis, and then your B, where it crosses over your y-intercept. So we can determine graphically from the integrated rate law, we can determine graphically whether it's a zero, first, or second order just by which one's a straight line. So if we're given a problem such as this. This is 2011. They give you these three graphs. Okay? So there's the equation. They give you these three graphs. Given that the reaction is 0, order 1, or 2, use the information to respond. Determine the order of the reaction with respect to ethanol. Ethanol being the only reactant. Well, which one of those is a straight line? The first one. What's the y-axis on the first equation? Okay? It's just the concentration of ethanol. This is 1 over the concentration of ethanol. This is the natural log of ethanol. Well, which order gives us a straight line if it's just concentration versus time? 0 order. So I can tell just looking at the graph that it's 0 order because that's the one that's a straight line. Now, if you go and you look on your equation sheet, didn't somebody say they had their Princeton review right there out somewhere? Okay, well, I got mine. Okay. So if you go and you look at your, equation sheet, your formula sheet, okay? You look at the equation sheet for kinetics. They give you these equations. Now they don't give them quite in the same thing, but just move the plus AO plus, we just move this one over to the right side. Okay, can y'all see? I mean, all the minus one. So to get the equation that you're looking at in your notes, concentration is equal to negative KT plus the initial concentration. Natural log is equal to negative KT plus the natural log. Just put it all over on the right hand side. Y'all following me on that, right? You guys looking at me like a cow looking at a new gate, like how'd that get there? You go. All right, so we can get these equations. So the equations are given. Now they don't tell you which one is 0, first, or second order. But they list them, 0, 1, 2. Okay? So even though they don't tell you which one it is, it's in order. 0 order, first order, second order. So we can just look at the graphs and we can determine the order of the reaction just by looking at the graph. So if I look at this graph here, this is year 2015. What's the order of the reaction going to be? Okay, we're just looking at, well, you got all three graphs, but look at the y-axis. Okay? This is absorbance, or in this case, that's the exact same thing, kind of concentration, because the concentration and absorbance are directly proportional. You just have absorbance, concentration, natural log of concentration, 1 over concentration.
First order,
How do you know that?
because the natural log plus it's like a straight line.
Because this is the one that's linear. The one that shows up linear is the one that's following the y equals mx plus b when you graph the data. So that means it's first order with respect to whatever OCL minus. Okay? So you just look at whichever one is straight, follows the y equals mx plus b. We can determine the order of the reaction using this integrated rate law just from the graph. Okay? Uno más. Notice how many there are on the AP test. These are all over the AP questions. What year is this, 16? Yeah. Okay? So now I'm going to look at these three graphs. Okay? So I have concentration here. I got natural log of concentration, and I have 1 over concentration. Which one's linear?
I'm in the third, I'm so sorry.
Which graph?
The third.
Bottom graph, but since it's 1 over the concentration, that means it is second order. Now again, if you don't want to, you don't have that memorized, or you get all confused. Is it log? Is that first order? Is that second order? Is it 0? Which you go to the equation sheet, and it's giving you right there, listed in order 0, 1, 2, and then you just look at what the y value is. Is it just concentration? Is it just natural log, or is it 1 over?
We'll never have third order or fourth
No,
order.
no.
Your phone is low battery again.
Okay. It's still videoing though. It's fine. That's all right. Okay, so the first thing that we can do with the integrated rate law is we can determine the order of the reaction from the graph. And again, we don't have to memorize it. But if you turn in your notes to page 15, you have the little table on the bottom. It kind of summarizes all that. And I made it color for you to stand out. So if it's 0 order, the rate's just gonna equal K. Concentration is gonna be negative K, there's your equation for it. It's gonna be, you're gonna just graph concentration versus time is gonna give you the straight line, okay? The slope is gonna be negative K. The slope is always gonna be K, but the K is always positive. K is always gonna be a positive number. K is never a negative number, so, but the slope, and you guys know when you have a positive slope, negative slope, right? So the slope is always gonna be K, it's always gonna be the positive value, whatever it is. And then the half-life, this equation right here is given to you. And when we look at the math of that, this comes from the first order. This equation right here is also on your kinetics. It's right there, it was on the exact same place where we were just looking at the other one. And then here's the half-life here, but you're never gonna have to do half-life for 0 or second. They only give you the equation for first. So what does it mean half-life though? For half of the reactant to go to products. Okay? So if you start with 1 molar, after 1 half-life, it's gonna be 0.5 molar. After a second half-life, how much are you gonna have? 0.25. And you can calculate that, and this is just really a mathematical thing, okay? And we'll start with that on Monday. All right, so y'all, you have a great weekend, and go Jags.
You gotta end it.
Okay. He's not letting me end it.
Are we, is Vlad the crystal violet one?
No, but it's